Okay, the next connector, moving on with connectors, is a roller. And I already mentioned the symbol. It's kind of hard to see on this video, but when you draw it freehand, it looks like a triangle on two wheels. Forces are normal to a roller. We presume zero friction. A roller or a pin confined in a slot, same idea. The force is only normal to that. A rocker, same thing. Force is only normal to the point of contact. Normal to the surface at the point of contact. Smooth contacting surface, same thing. You can see how a lot of these situations are very much alike. A collar on a smooth rod. And by the way, let me back up for just a second. Smooth contacting surface, frictionless. Think frictionless. Collar on a smooth rod. Forces are perpendicular to the rod. The reaction forces are perpendicular to the rod in equilibrium. Okay, a pin. Now, forces can be in two directions. Zero moment, no moment. Because if you applied a moment, it would rotate. No moment. By the way, that's what happens in the other situations too. You'll have a reaction moment. You can have a reaction moment around this, like so. By the way, I'll hasten to point that out. This one, though, if you have a moment, it will it'll move, so it's not in equilibrium. Same thing here. If it has a moment, it'll move. If it has a moment, it'll move. If it has a moment, it will move. And then these, if they have a moment, they will move. I want to take a look a little closer at this situation. There we go. Let's erase this. Now, the way this is drawn, this is a collar with a pin through it. And of course, let's go back to a pin. Where's my pin joint? Oh, the pin joint's next. If you have a moment, it's going to move. So there can't be any reaction moments in equilibrium. The way this is drawn, there's a pin here. So the way this is drawn, there's only forces, no moments. If there weren't a pin there, if it was a fixed piece, then it would have a moment. So understanding, the idea is to understand what do you have. So here's a member, keywords, pin, connected. If it was fixed connected to a collar, it could have a moment. Pin or hinge, no moment. It would move if it has a moment. And we're trying to find the conditions where it doesn't move. No moment around a pin and hinge. Now, this is what I was talking about earlier. This can have a moment. Perpendicular force and a moment. And a fixed support. Forces, two forces and a moment. There's three equations. Remember, an equation for the total force in the y direction, the total force in the x direction, and the total moment. We get three equations when we're dealing with 2 dimensions. In 3 dimensions, there's 6 equations. Here's some examples of supports. So here's a cable. You can see, barely see the rocker. So this handles expansion joints. But this is just a girder resting on a ledge, which you consider to be a smooth, frictionless surface. Pin support right here, and these are all fixed connections, welded together. And if you're not careful like I was, something can break. A roller, fixed, a pin. So here's the physical construction of a pin. Usually we denote a pin just by drawing a dot to mean a pin. Fixed support. Most of the time with fixed supports, we'll do this little diagram here. This is just another example of a free body diagram I forgot to remove when I was editing the slides, so I'll have to remove it later. Ignore that man behind the curtain. Okay. Center of gravity. Weight can be considered to apply at the center of gravity of an object. Gravity acts at all points on this body, but it's a distributed load. Remember, we talked about distributed loads. So W can, due to the center of gravity, can be like this. X bar is the center of gravity. And we can consider all the force, the area under this curve, to be concentrated at the center of gravity. Center of gravity is just like we calculated it. The integral xw dx over the integral of w dx. So, but we skip the calculations. We say, okay, if we know the center of gravity and we know the weight, we can just put the force there. We don't have to go through all these machinations, all the calculations. So in your physics classes, that's what you've been doing all along. You've just been treating the weight as acting at the center of gravity of an object. But that's what we mean by the center of gravity. Okay. These models are ideal. They aren't really rigid, but pretty close. Most materials, they start to either deform or break at only 0.1% of change in length. In other words, a body which is constant length is a pretty good approximation. That if you pick 2 points inside a body that their relative coordinate with respect to each other is unchanged, is a good approximation. Rubber bands, not such a great approximation. We have to handle things like that a little differently. Idealized supports. So here's a beam, for example. We think of one end as being fixed, like so. The other is just resting over here, which we say, oh, that's a roller support. So this denotes a roller support. If I draw something by hand, I would probably draw a roller support like this. It's just another way to draw the same symbol. This crane, pin supports, pin, what is this pin holding? I don't know. Pin, link. So when analyzing this, we would, we could have A and B forces at the 2 pins, X and Y forces, that is, X and Y forces at the 3 pins. But the force from C to B has to be collinear with C and B because it's a 2-member link. And, okay. So draw the free body diagram of this 2-member beam. That should be real easy for you guys. So at 3 meters, we would have W. And W equals 100 kilograms. Then we'd have AY acting here, AX acting here, and a moment at this fixed support. So I'm drawing my free body diagram right on the picture, by the way. That's okay to do. You're okay to do that. So we know that AY has to be equal and opposite to 1200 newtons plus 981 newtons. I should say, I shouldn't use the symbol W. I should say mass equals 100 kilograms. Weight is going to be 981 newtons. And so AY is going to have to be equal and opposite to that. AX equals 0. There's no other forces in the X direction. AY would be equal to a positive 981 plus 1200. AY minus 1200 newtons minus 981 newtons equals 0. So AY would equal 1200 plus 981, which works out to be 2181 newtons. And we have to set the moments equal to 0. We have two moments. Sum of the moments equals 0 equals the reaction moment I'll call this M sub R. Minus 1200 times 2. The 1200 newtons is acting to move the system clockwise. So it'd be a negative quantity. Minus 981 times 3. And the units would be Newton meters. Okay, let's crunch the numbers, find out the answer to this guy. So, crunching my numbers in my calculator here, I get 5383 newtons. Okay, and they're going to go through this. Weight, 3 meters from the beam, and so forth. What they're drawing here is nearly identical to what I did. Now, let's do this one. They just didn't run through, the book didn't run through the numbers, by the way. So, let's do this one on the next video.